I want to talk today about predicting trends in physical properties based on the intermolecular forces of the molecules that we're looking at. And the steps that we want to follow for something like this, we're going to start by determining the most important intermolecular forces in the molecules being compared. This requires us knowing the three-dimensional structure of the molecule, so we're going to have to draw a Lewis structure of the molecule. We're going to arrange the molecules being compared in the order of increasing IMFs, and we want to remember that most of the physical properties, though not all of them that we look at, the trend will either go in the same order or in the opposite order as the IMF. We want to remember the following. For a boiling point and freezing point, as the IMF increases, the molecules are held together more tightly, so the IMF and the boiling point or the freezing point go in the same direction, and when one goes up, the other goes up. This is also true for viscosity. So as the IMF increases, the molecules are held together more tightly. They slide over each other with less fluidity. It's harder for them to slide over one another, and the viscosity increases. Oops, I forgot one of my arrows, so this arrow should be here. As IMF goes up, viscosity goes up. For vapor pressure is a measure of the amount of vapor generated by a substance at some temperature. The weaker the IMFs are, the less holding the molecules together, the more readily they vaporize. So the vapor pressure goes up. So the vapor pressure actually goes in the opposite of the IMF. Lower IMF means greater vapor pressure. Greater vapor pressure means a lower boiling point, and that's something people confuse a lot as well. So if we look at an example of this, let's arrange the following compounds. Let me change this view a little bit, get rid of the crosshairs. Let's arrange the following compounds in order of increasing boiling point. So we've got silicon tetrafluoride, nitrogen trifluoride, and ammonia. The first thing we want to do is come up with accurate Lewis structures of all three of these, and these are the Lewis structures. And what you'll see is that silicon tetrafluoride is a tetrahedral compound, and it does have polar bonds in it, but the dipoles from all of these polar bonds cancel out, and there's no net dipole, so we only have LDF in this molecule. On the other hand, for the tetrahedral nitrogen trifluoride, there is a net dipole. You have dipole-dipole interactions. And finally, ammonia is also tetrahedral, but the most important, so it would have dipole-dipole interactions, but the most important thing going on here is hydrogen bonding. And what we want to say is hydrogen bonding is stronger than dipole-dipole interactions, which are stronger than LDF. So silicon tetrafluoride is going to have the lowest boiling point. It's got the weakest IMF. Nitrogen trifluoride is the next because it's got dipole-dipole, which is weaker than the hydrogen bonding in ammonia.